Okay, so this was the example that we did on Wednesday, right? So we said, what I have here is a Fourier series. All right, what makes this guy a Fourier series? What's it mean to be a Fourier series? It's to say that S of t is a periodic function that is the sum of a bunch of sines and cosines, okay, that are harmonically related. What did it mean to be harmonically related? Frequencies are integer multiples of each other, okay? Frequencies are integer multiples of each other. So what we went through last time is we said, all right, this guy has, this is a periodic function. This is what that function looks like if I draw it, right? And what we see here is the period basically is from, this peak to this peak. And we said that that period there was 4 milliseconds, right? Which gave me what we call a fundamental period, which I wrote as f sub 0 of 250 hertz. All right, that's the fundamental period. In other words, that's the basic timing of this thing. And he has higher order harmonics, right? So those harmonics are integer multiples of that. The fundamental term is also sometimes called the first harmonic. All right, so 1 times that is the first frequency. And then we said here we got 1,000, 1,750, and 1,500 in this case, right? So in this case here, what this f equal to 1,000, what do we call that? If the fundamental frequency we figured out was f naught equal to 250 hertz, what's the what would be the term at f equal to 1,000 hertz? What do we call that? What do we call the term at f equal to 1,000? Let's put it this way: how does 1,000 relate to 250? What's fourth? Yes, it's the fourth harmonic is what we call it. Yes. So this guy's the fourth harmonic. Now, what do we call this 10 here? What's the frequency of the number 10? I guess I got it written there, but what's the frequency of the number 10? It's 0, right? Why do I say it's 0? Why does a constant have 0 frequency? Yeah, it doesn't repeat, right? So it's basically, to say that it's periodic is to say that, I only need to go infinitesimally over it for it to be the same value again. The definition of a periodic function is that x of t is equal to x of t plus t, right? This guy is got no variation whatsoever. All right. To say that something is AC just means that it has periodic variation. Does not have to be a sine wave. All right. Does not have to be a sine wave. Just means that it has to have periodic variation. All right. So we figured out the fundamental period, which I did from that graph. The other thing I said the other day is I can use this greatest common divisor because the greatest common divisor are the terms that I've got. Not a common thing to do particularly, but I said that this is how you would call it. Okay, and this is in the notes that I posted from Wednesday. All right, the next part of the problem I said was to determine the highest harmonic in this thing, which we determined was 7, right? Because 7 times 250 is 1,750. So that's the highest harmonic this guy has. Okay. Now, we said is the Fourier series can take several different forms. Okay. And these are the forms that it can take. So we can express a periodic signal as the sum of a bunch of sines and cosines at these integerly related frequencies, right? Or we can use this, what I called shifted cosine version, or we can use the complex form of the series. All right. What I did was we're ultimately going to work with this one the most. Okay. Now, what we went through in class the other day, you can go back and look at it, is we went through then and we figured out the A, the B, and the C values, and the theta or the phi values. The other thing we wanted to figure out where I stopped was the alpha values, right? So what we say is we've got these relationships that exist for all of the different ways that we can view a single cosine. Okay. So what we know is that the this approach number 3 that I have here, where I think of it as 2 rotating vectors. Well, how did I get to that whole thing? what identity, what formula gets me to that third approach? Euler's identity, right? Euler's identity told me that a cosine at a single frequency is basically just the result of two complex vectors rotating, one of them clockwise, one of them counterclockwise. And the coefficients alpha 1 and alpha 2 are basically given by these things here, right? These relationships. And alpha 1 and alpha minus 1. Now the question is, what do I mean by alpha 1 and alpha minus 1? Well, I am specifically referring to the fact that this alpha 1 is for the positive first harmonic frequency, and this guy is for the negative harmonic frequency. Okay, so let's unpack that for a minute. All right, let's say I have let's say I have this particular example. Okay, all right, 3 cosine omega t plus 45 degrees. Now I want to put this, as I said, my approach 1. I want to put this into that approach 3. All right. If I gave you that and I said, give me this in that same form, alpha 1 e to the j omega t plus alpha minus 1 e to the minus j omega t, how would I do that? How would I figure out alpha 1 and alpha minus 1? Well, we use Euler's identity, right? What's Euler's identity tell us? What would those coefficients be? 1/2 the amplitude, so 3/2 times, and we can take it slow, e to the j omega t plus what? Plus 45 degrees. What do I do with the other term? It's conjugate, so it's 3/2 e to the negative j omega t plus 45 degrees. Like that. Okay. So I can rewrite that as what? 3/2 times what? What do I, so to get it into this form, to match that form, what do I need to do to that e to the j omega t plus 45 thing? They'll take the real part of it. So I want to get the e to the j omega t by itself. So what do I do with the 45, right? I have e to the j omega t plus 45. Yeah. I can write that as e to the j 45 times e to the j omega t. Like that. And then with this guy, 3/2 e to the negative j 45 degrees times e to the j negative j omega t. Okay. So when I look at this and I say this guy is for n equal to 1. This guy is for n equal to -1. Because the general form of this Fourier series, as we said, this guy could be written as the sum from n equal -infinity to infinity, alpha n e to the j n omega naught t. In this case, that is alpha minus 1 e to the minus j omega naught t plus alpha 1 e to the j omega naught t. Like that. You guys follow me? So what I did, so this is the first time I've used that formula, right? But I've only kind of thrown it up there, and I haven't asked you any questions about it yet. There's not even anything on the homework about this here. What I've just been doing is saying, okay, here's the formula, or here's a periodic waveform. You tell me the coefficients. Okay. So in this case, this is in that shifted cosine form. And I've said this guy can be expressed as a Fourier series in complex form like this. And the harmonics that are, since there's only one cosine, this guy only has a fundamental. He doesn't have any harmonics. Okay. What if I had said to you, okay, I have this. All right. 2 plus 3 cosine omega naught t plus 4 times cosine 3 omega naught t. What is that? How many terms do I have in that? How many harmonics are present in f of t equal to this? How many frequencies are there? Yeah. So this was tricky when I get to complex. Yeah, you're right. In the complex form, there's 5, right? When I just look at that waveform, you say, well, it looks like I got something with f equal to 0, right? It looks like I've got something at, let's say, I'm going to write it in terms of the harmonic numbers. Let's say, right, n equals 0. This is n equal to 1. What's this guy equal to? N equal to what? 3. It's the third harmonic. Okay. So if I were to expand this out, I'd say, all right, well, this looks like what I have is an alpha 0 term plus alpha 1 e to the j omega naught t plus alpha minus 1 e to the negative j omega naught t plus what? What else do I add into that? Alpha 3 e to the j 3 omega naught t plus alpha minus 3, yeah, e to the negative j 3 omega naught t. All right. That's the relationship that we've got there. Okay. Now, what we're gonna look at next week, right, is we're gonna look at, okay, how do we get to more complex forms of these things? In particular, how do I look at something like where I have that square wave that I showed you, right, where it's high, low repeating? How do I start from this and determine what the alpha n values are? Right, that's the useful thing typically, right, is that I'm giving you a waveform and you figure out what that is. And that's, I showed you before this thing called the FFT, right? I showed you on my phone where I took the FFT of my voice. That's what the FFT is doing, right? It's the one of the F's in the FFT is Fourier, right? So what it's doing is it's figuring out the those coefficients. So when you look at that graph, it's showing you the coefficients of that periodic waveform that's coming from my mouth. All right. All right. So I didn't want to cover a whole lot of new stuff today. Just want to make sure you guys were